Yeah. So today we will discuss unbounded solution. What do you mean by unbounded solution in graphical method? Okay. Just give me a minute. Yeah. Unbounded solution. Okay. So in the previous session we have discussed alternative optimum solution. Explained with an example. So now in this session we will discuss about unbounded solution. So what do you mean by unbounded solution? So LPP means what is it? LPP consists of objective function, and constraints will be there, and decision variables will be there. So I will write decision variables. Okay. Now I will tell you what do you mean by unbounded solution. So when the value of objective function, increases, when the value of the objective function increase infinitely, okay na? If the values of the decision variables also increases infinitely, then that such type of LPP circle has unbounded solution. So what do you mean by unbounded solution? If the value of the objective function increase infinitely, when the decision variables also increases infinitely of an LPP, then the solution is called an unbounded solution. Okay, I think all of you understood. If it is maximization, if it is minimization, the value of objective function decreases infinitely. Okay, so when the values of the decision variables increases or decreases, no problem. So whenever the decision variable values are increases, obviously objective function values are also increases. Such type of an LPP has an unbounded solution. So I will explain with an example, then you can understand better. Okay, so write down. This is also graphical method, one of the exceptional case or special case of graphical method. So the same steps will be there, what we are using in graphical method. So I will explain this unbounded solution now with an example. Write down. Solve the following LPP. Solve the following LPP by using graphical method. Solve the following LPP by using graphical method. Solve the following LPP by using graphical method. At maximum z equal to 6x1 plus x2. 6x1 plus x2. Maximum z equal to 6x1 plus x2. Maximum z equal to 6x1 plus x2. Next one, subject to the constraints. Write the first constraint 2x1 plus x2. 2x1 plus x2. 2x1 plus x2 greater than or equal to 3. 2x1 plus x2 greater than or equal to 3. Second constraint x2 minus x1. x2 minus x1 greater than or equal to 0. And how many decision variables are there? And x1 comma x2 greater than or equal to 0. x1 comma x2 greater than or equal to 0. Same concept as it is. What is the step number 1 in graphical method? Convert all the inequality constraints into equality constraints. Convert all the inequality constraints into equality constraints. That is step number 1. Step number 1, convert all the inequality constraints into equality constraints. Convert all the inequality constraints into equality constraints. Then we get 2x1 plus x2 equal to 3. Equation number 1, and x2 minus x1 equal to 0. Equation number 2. Next step number 2. Plot each equation on the graph. As each one will geometrically represent a straight line. If you want to plot these equations on the graph, you require the points. So first you have to identify the points. So how will you identify the points? Consider equation 1. Put x1 equal to 0. So equation equation 1, put x1 equal to 0. That means what we get x2 equal to p. x2 equal to p. Same equation, put x2 equal to 0 now. x2 equal to 0. x2 0 means what is that? x1 equal to 3 by 2. 3 by 2 means 1.5. So now I got the first point. What is the first point? x1. x1 value is 1.5. x1 value and x2 value is 3. So the first point is 1.5. 1.5 comma 1.5 comma 3. The first line is completed. Second line, same as this. Consider equation 2. Consider equation 2. Equation 2 directly you will get. What is the point you are getting? 0 comma 0. Simply put x1, otherwise you can write put x1 equal to 0, implies x2 equal to 0. Put x2 equal to 0, x1 equal to 0. Simply x1 equal to x2. x1 equal to x2 means it divides the origin. Okay? Divides the origin into two equal parts. Both are equal amount. 0 comma 0 origin. Wait point. So what's the point you are getting? 0 comma 0. 0 comma 0 is the point. Okay? Now I know the 2 points. 1.5 comma 3, 0 comma 0. Okay? Now I can draw the graph. So what is the maximum value? Maximum value is 3. Up to 3 you can consider the scale. Up to 3 you can consider the scale. So 1.5 comma 3, 0 comma 0 are 2 points. Just taking x-axis. This is x1. This is x2. This is origin both. Okay. So 1, 2, 3. This is also 1, 2, 3. So first point 1.5 comma 1.5. So this is 1.5. So 1.5 is this one, and 3 is this one. 1.5. So join these points. This is line 1. Line 1. Next second point. Second point is what is 0 comma 0. 0 comma 0 means between x1 0, x2 0. So this is x1. x1 0, x2 0. So from this use the scale. So this is equation 2. This is equation 2. And now you have to identify the common region or feasible region. How will you identify the common region? I have already told. What is how will you identify the common region? If the constraint is less than equal type, below the line is shaded. If the constraint is greater than equal type, above the line is shaded. Okay. So now both the constraints are greater than equal type. Greater than equal type. See this one. This is the first line. Greater than equal type is above the line is shaded. First line is greater than equal type, above the line is shaded. Okay. Second line is also greater than equal type. So greater than equal type means this is the line. Okay. Now, so above means this one, below means this one. Okay. So above means the second constraint is also greater than equal type. Greater than equal type is above the line is shaded. Above the line is shaded. Now what is the feasible region for this one? So this is not a feasible region. This is not a feasible region. This is not a feasible region. Both the lines are here. So this all comes under feasible region. If you extend it, it goes infinite. It goes infinite. But all everything is you can extend these lines. You can extend this x-axis, y-axis, or the x2 axis. You can extend. Okay. So all this is called feasible region. All this is called feasible region. Now what are the points you are getting from feasible region? A is 1 point I am getting. B is 1 point I am getting. So remaining points I am not getting the edges. So only I got A and B. A and B. Okay. Now the concept, same concept. So assume that you have got A and B are the only points in the feasible region. You are not getting any other points. So what is the feasible region? Simply as the previous problems you have done the same concept. So you can say AB is the feasible region. AB is the feasible region because only you are getting 2 points. You are not getting the 10 points. So simply I will write AB is the feasible region. And you are saying that for this problem you are saying that AB is the feasible region. We have to check whether it is a feasible region or not for this particular. It is a feasible region. You can identify the points and you can say that optimum value gives at these points only. So we verify. Okay. So AB is the feasible region. We got it. Okay. Step number 4 is nothing but you have to identify these points. So I will identify as usual. So A point I will identify, B point I will identify. That is step number 4. Step number 4. A is the intersection of 1 and 2. If you solve 1 and 2, you will get the A point. So A equal to intersection of 1 and 2, intersection of 1 and 2. Okay, so see the first equation. What is the first equation? We have 2x1 plus x2. Yeah, 2x1 plus x2. Write the first equation. 2x1 plus x2 equal to, this is the first equation. And second equation, actually x2 minus x1. I will write in order. In order, if you write what is that, minus x1 plus x2 you will get is equal to 0. Is equal to 0. This is equation number 2. Solve these equations. So just put minus. So minus, minus, minus. So then x2 minus x2 get cancelled. So 2 into minus of minus is plus. So 2 plus 1. 2 plus 1 is 3x1 equal to 3. That is what is x1 value? x1 value equal to 1. x1 equal to 1. If you substitute any one of the equation, you will get the remaining value. So I will take right here from 2 equation 2. I will substitute. What is equation 2? This is equation 2. Minus x1. You got x1 value, so minus 1 plus x2 equal to 0. So that is what is x2 value? x2 value equal to 1. x2 value is equal to 1. Okay. So that is what is the A point I am getting. A point I am getting is x1 value is 1, x2 value is 1. A point is 1 comma 1. And next you have to identify the B point. I think you have completed this one. So now I got the A point. What is the A point you got? So just I am writing here. A point I am getting is 1 comma 1. Next B is the y-axis point. So obviously 0 comma A. 0 comma A means what is the B equal to 0 comma what is this value? 0 comma 3. Now step number 4 is completed because you are saying AB is the feasible region. So I have identified a corner point of A and corner point of B. Now step number 5 is nothing but whatever your objective function is given, substitute these points in the objective function, go for maximum value because objective function is maximum. It is given. Right. Step number 5. Step number 5. Step number 5. Here I write step number 5. Step number 5, what is given? Given that right here. Step number 5. Step number 5, given that maximum z equal to what is the function given to you? Maximum z 6x1 plus x2. 6x1 plus x2. 6x1 plus x2. First I will calculate ZA point. That means 6 into 1 plus 1. That means what is the value? 7. Value is 7. Next I will calculate ZB. ZB is 6 into 0 plus 3. That means value is 3. What is your objective function? Generally what we will do, your objective function is maximization or minimization. You are saying that maximization. So what is the maximum value here? 7. That means you are saying that for this particular LPP, the maximum value of z equal to 7 at the point A. What is the A point? 1 comma 1. But it is not correct. Why it is not correct? If I prove one point, if I substitute that point in the objective function, it gives more than 7. Then automatically this one is wrong. So if this is correct, what is the for any point for this LPP? For this LPP, there is no other point which gives the maximum value of 7. If any one point exists, if you substitute that point in the objective function, if you get more than 7, then automatically this one is wrong. So that means if I prove only one point is enough to prove. If I substitute that point in this objective function, if I get more than 7, obviously you cannot say that maximum value equivalent to 7. Okay, so that means, so I will take an example. So what is the feasible region? This is the feasible region we are getting. And what we understood? A point. What is your A point? 1 comma 1. 1 comma 1 exists in this feasible region. This is 1 comma 1. This is 1 comma 1. 1 comma 1 exists here. This is 1 comma 1. I think we are able to hear. This is 1 comma 1. Just I have rounded 1 comma 1 exists in this feasible region. Similarly, 0 comma 3. 0 comma 3. This also exists in the feasible region. So there are so many points existing in this feasible region. I will take, so for example, say this one. This is 1 comma 10. If you go on like this is an infinite feasible region. 1 comma 10 exists or not? It exists. 1 comma 10 exists. 1 comma 9 exists or not? It exists. 1 comma 7 exists or not? It exists. Suppose here 2 is there. 2 comma 8 exists in this or not? 2 comma 8 exists, 2.7 exists, 2 comma 7 exists. Okay, and 3 comma 5 exists, 3 comma 5 also exists. So there are so many points that exist in this feasible region. And what you are saying for this particular problem, in this feasible region, you are saying that maximum value of z equal to 7 at this point only, a point only. What is it? A point 1 comma 1. So what I will do now, I will take 1 point. I will take 1 point in this feasible region. If I substitute the point in this objective function, I will say you will get more than 7. You will get more than 7. 1 point is enough to prove that one. Okay, so that means there are so many points exist. So if you substitute those points in the objective function, then automatically we get maximum value of z is more than 7. So I will take one example. For example, I will consider a point. I will consider a point 3 comma 8. I will consider a point 3 comma 8. 3 comma 8 exists in this feasible region or not? Suppose 3 is here, 8 is somewhere here, 3.8 exists. So 3.8 exists here. So you can take any point in this feasible region, so that maximum value of z equal to more than 7. Z is more than 7. So 3 comma 8 exists in this feasible region. So if I substitute 3 comma 8 here, what you will get to see? Maximum z equal to what you will get? 6 into 3 plus 8. That means 18 plus 8. 18 plus 8 means what is it? 26. So 26. And which is more than 7 or not? And there are so many points. Which gives maximum value of z equal to 7. So this type of solutions are called, this type of LPP has an unbounded solution. So what do you mean by unbounded solution? That's why definition I have told. What is that? When the objective function, the value of the objective function increases infinitely. When it increases, if the decision variables also increases infinitely. So that of an LPP, such an LPP has an unbounded solution. Right? So after this, step number 5, write out. The given LPP has, after step number 5, don't write this one. After this one. Okay. So write. The LPP has an unbounded solution. The LPP has an unbounded solution. LPP has an unbounded solution since there exist. Why it is called unbounded solution? Since there exist number of points in the feasible region. Number of points in the feasible region for which the value of the objective function is more than 7. Value of the objective function is more than 7. Full stop. For example, any one example is enough. 1 point is enough. You can consider any point in this feasible region. You don't want to consider 3 comma 8. Someone will consider 2 comma 10. Someone will consider 1 comma 9. No problem. Which is more than 7. Okay. More than 7 point you have to consider. Okay. For example, consider a point 3 comma 8 in the feasible region. 3 comma 8 in the feasible region. 3 comma 8 in the feasible region. 3 comma 8 lies in this feasible region or not? 3 comma 8 exists in this feasible region. Then the objective function value at this point is maximum z equal to 6 into 3 plus 8. 6 into 3 plus 8, because this is the objective function. 6 into 3 plus 8. That means what is the value you are getting? 26. 26, which is more than 7. And that means what is that? If the values of the decision variable increases, obviously objective function value also increases. Okay. So therefore, the given LPP has an unbounded solution. So what do you mean by unbounded solution? Unbounded solution means when the value of the objective function increases infinitely. How it is increases infinitely? If the values of the decision variables, based on the decision variables only, objective function will increase. But the decision variables values are also increases indefinitely, like infinitely. Okay, of an LPP. Such an LPP has an unbounded solution. Such an LPP has an unbounded solution. So we have completed alternate outcome solution and then unbounded solution. In the next class, we will discuss about infeasible solution. The last one in graphical method we will discuss is infeasible solution.